High above Earth, we gain perspective. Just as day follows night, we move naturally from darkness into light. That faint blue glow is all that separates us from the void of outer space. Within that thin layer of atmosphere, life as we know it evolves. Below us lies the Amazon rainforest, a hotspot for life on Earth. Its billions of acres of trees and plants exhale a fifth of Earth's oxygen. Even from space, life colors Earth. The snowy peaks of the Andes mark the edge of this vast continent. But as we head across the Pacific Ocean, we will seek other islands of life that dot our globe. The Galapagos provided a secluded laboratory in which Darwin could observe life in the process of changing and adapting to survive. Darwin's theory of evolution arose from this exotic port of call. All around us lies water. It covers 70% of our planet. Water courses through every living organism, and indeed, life itself began in Earth's oceans. Earth is truly a water planet. But water also isolates island from island, allowing landlocked species to branch into a riot of biological diversity. This vast watery divide makes for spectacular evolutionary variety, but it also makes islands vulnerable to change. The warm, shallow waters around the Philippines provide a home to the world's most diverse coral reefs. But the delicate organisms have suffered from rising sea temperatures and destructive fishing practices. Nearby, the teeming rainforests of Borneo face threats from deforestation and also from new species introduced by civilization. Natives must now compete with alien settlers for limited space and resources. We're over the Indian Ocean now. Just off the east coast of Africa, the vibrant rainforests of Madagascar have been decimated by deforestation, as if the island itself were shrinking. As we pull back farther, we realize that Earth, too, is an island in space. With the help of remote cameras, we see beyond our own small part of the world. Weather satellites like this one allow us to check the local weather for the whole planet. A vast network of satellites allows us to monitor the environment hour by hour, day by day, year by year. A new picture of Earth is emerging. A digital Earth, made up of color-coded representations of our planet's vital signs. We can now take the temperature of the watery skin of our planet. The vivid colors you see engulfing Earth's oceans represent the temperature of the water's surface. Cool blues and greens show regions where the sea surface drops to near freezing, while oranges and reds show spots as hot as a warm bath. When the tropical Pacific warms or cools by just a few degrees, weather patterns around the world can change dramatically, causing floods in some regions and droughts in others. Our electronic eyes in orbit also look at the makeup of our atmosphere. We are seeing the concentration of carbon monoxide, color-coded red at its highest, blue where hardly any is measured at all. The burning of plants or fossil fuels produces this toxic gas. In Central Africa, farmers burn pastures to clear them for planting, releasing large quantities of carbon monoxide. Such human activities show up deep red on our digital Earth. Our eyes in space have changed our perspective on this fragile planet, but we also look outward. What can we learn about life as we look beyond Earth? It took the Apollo crew more than 4 days to travel to the moon. It takes light about 1.5 seconds to skip that stone. As we continue our journey, we will use light's more efficient measure to chart our progress. The moon is a good neighbor, but not a lively one. Thanks to the moon, Earth's rotation remains stable and we have regular tides. But the moon is too small to exert enough gravity to hold onto water in a protective atmosphere. And both are necessary for life as we know it on Earth. If the size of a world is important to life, let's venture a little farther in our planetary neighborhood and find something more in our weight class. If we're the third rock from the Sun, how about rocks 2 and 4? The lines we see overhead track the motions of the planets in our solar system. We're heading in, closer to the Sun. Venus is nearly Earth's twin in size, only slightly smaller. But this cloud-covered second rock receives about twice as much sunlight as we do. That means it's hotter. Below those clouds, any similarity to Earth sizzles away. Greenhouse gases trap sunlight and temperatures soar to 900 degrees Fahrenheit. Air pressure on Venus is about what a deep-sea diver experiences a mile below the ocean's surface. High temperatures and pressures make Venus an unlikely hideout for life. So what about the fourth rock from the Sun? To check Mars for signs of life, we have to travel much farther, where sunlight is only half as intense as on Earth. Mars is small, only half Earth's size in diameter. And tiny Mars has a hard time holding on to more than a thin layer of atmosphere. But long ago, things were different. Mars supported a thicker atmosphere, and water may have flowed on its surface. Billions of years ago, Mars may have offered a better habitat for life than Earth. Now the Martian landscape is dry and frigid. Visiting spacecraft have uncovered evidence for ice near the surface. But digging for life will have to go deeper. If the red planet harbors even microbial Martians now, they would require liquid water for sustenance, which could possibly exist deep underground. Venus is too hot, Mars is too cold. Earth is just right. Did you know you were living on the Goldilocks planet? Each planet's distance from the Sun is critical to its potential for life. Venus is too close, and Mars is too far. We can think of their orbits as staking out the inner and outer boundaries of a territory friendly to life like ours, something scientists call a habitable zone. Earth orbits smack dab in the middle of this prime piece of solar system real estate, with just the right conditions for life. Unless we tip that balance, trapping too much heat in our atmosphere could change the equation for humans and for other life as well. But remember, life on Earth is also tough and resourceful. Within our habitable zone are creatures that survive boiling temperatures and undersea vents, and others that thrive in rocks more than 6 kilometers underground. So it might be wise to expand our search for life. Let's take a look even farther from the Sun. we're approaching Jupiter, a planet very different from our own. With no solid surface, the giant planet is the largest in our solar system, bloated with hydrogen and helium, and big enough to engulf more than 1,000 Earths. Life as we know it isn't likely to feel welcome here. But Europa, one of Jupiter's many moons, may tell a different story. About the same size as Earth's moon, Europa sports a thick coating of ice. Jupiter's gravity stretches and pulls the tiny moon, heating its insides. Below the icy surface, microbial life may flourish in a slushy ocean. Second only to Jupiter in size, Saturn with its stunning rings is another giant whose moons may be more hospitable to life than its wind-ravaged self. Enceladus is one of Saturn's life-likely moons. A mix of ice, dust, and organic molecules spews like a geyser from its warm south pole. Liquid water may not be far below the surface. Might this, too, be an island of life? What we know about the south pole of Enceladus comes from the Cassini mission. Cassini began its billion-mile journey in 1997 and entered Saturn's orbit in 2004. Filled with cameras and scientific instruments, it has been sending data back to Earth ever since. Long-haul trips that take years or decades would tax a human crew beyond its limits, so our robot spacecraft make the journeys instead. If Cassini had been traveling at light speed, it would have made its 7-year journey in little over an hour. No wonder people dream of traveling at the speed of light. So far, we have launched 5 spacecraft, moving fast enough to escape the sun's gravity. One day, they will leave the solar system altogether. But as of today, none have traveled more than about 16 light hours from Earth. To think, no spacecraft has yet traveled as far as light travels in a single day. We have now reached the outer limits of our solar system. We're surrounded by a cloud of icy particles, tiny comet wannabes, leftovers from the formation of the solar system. In about 15 minutes, we've come almost the distance that light travels in a year. On our journey, the laws of physics won't limit us. Our minds outpace the speed of light. Human intellect and imagination allow us to transport ourselves virtually to the far reaches of outer space, and we have much farther to travel today. Hang on to that heady thought as we accelerate. We are speeding out of our solar system and nearing our closest starry neighbors. That's Sirius, 8 light years from home, and Procyon at 11. But Alpha Centauri is our closest stellar neighbor at only 4 light years away. Some stars out here have their own planets, just like our sun. These planets around other stars are called exoplanets, and astronomers began finding them in 1995. Within a decade, astronomers had discovered nearly 200 of these alien planetary systems. Today, we know of hundreds more. Each blue marker corresponds to a star that hosts at least one exoplanet. Thanks to research teams and spacecraft missions, the rate of discovery continues to increase, with many new planets announced every month. Astronomers detect them by looking for a wiggle in the parent star, a slight back and forth movement caused by the gravitational pull of the orbiting planet. Sometimes exoplanets are detected when they pass in front of the parent star, causing a dip in its brightness. As you might guess, the bigger the planet, the easier to detect it. So we are finding more Jupiter-sized exoplanets than Earth-sized ones. We are also finding that some stars have more than one planet in orbit around them, just like our Sun. One star that hosts at least 4 planets is Gliese 581, about 20 light-years from Earth. All of its planets are bigger than Earth, but much smaller than Jupiter or Saturn. The star itself is tiny and dim compared to our Sun. Its planets would have to huddle close to it for any chance of Earth-like life to survive. That means its habitable zone is smaller and narrower than that of our solar system. We have sped up time in our view, allowing 1 month to pass in just a minute. We can see how quickly these worlds zip around their parent star. The outermost of the planets skirts the extreme edge of the habitable zone. Its orbit is highly elliptical, carrying it sometimes closer, sometimes farther from the star. If it were a small planet like Mars, this fluctuation would leave it out in the cold, with little to no chance of supporting a life-fostering atmosphere. But this super-Earth is large, at least 8 times as massive as our home world. It wields enough gravity to hold on to an atmosphere to keep the planet warm, even when it drifts farthest from its parent star. Life might just be possible here, where temperatures probably climb high enough for liquid water to flow. Based on our best understanding of such super-Earths, we can imagine what such a world might look like. A potential island of life in the cosmos. Gliese 581 is only one among hundreds of stars we've found to harbor planets. New ones are being discovered all the time. Our small sample only hints at the vast possibilities for life in the universe. The hundreds of planets we've discovered suggest that billions of planets could reside in our Milky Way galaxy alone. From out here, we can see a clustering of known exoplanets around Earth, not because they don't exist elsewhere, but because we've started the search in our own cosmic backyard. Welcome to our galactic hometown, the Milky Way, a thin plane of hundreds of billions of stars extending 100,000 light-years across. That means it takes light as long to beam across our galaxy as our species has inhabited Earth. Planets may be more abundant than stars in our galaxy. But every planet in the Milky Way may not prove an ideal life site. Stars close to the center of the galaxy are tightly packed. Crowding may make it harder for planets to coexist peacefully and survive long enough for life to evolve. In the outer reaches of the galaxy, a lack of heavy elements such as iron and potassium may not provide the right chemical ingredients for the elixir of life as we know it. But don't let these limitations discourage you. Our galaxy is only one among hundreds of billions of galaxies in the universe. Every point you see is not a star, but an entire galaxy of stars, each containing hundreds of billions, perhaps even trillions of stars. We have now traveled 60 million light-years from home. We're passing through the Virgo cluster, right at the edge of our detailed knowledge of individual galaxies. Past this point, we know only the most basic facts about these cities of stars, simple census data compared to the individual biographies of other galaxies. So let's turn home, Milky Way bound. We are aiming for a point about 2/3 of the way out from the center of the galaxy, on the outer edge of one of the spiral arms. We dive into the midst of the thousands of stars that spangle our night sky, a tiny fraction of the billions in the galaxy. We are back in our own solar system now, embraced by the reassuring orbits of our sibling planets. And finally, home, planet Earth, the one place where we know for sure life thrives in abundance. Our journey has allowed us to see Earth in a way we may not have seen it before, as a fragile island of life in a vast universe of possibility. We have gotten this far, farther than any other living creature we know. We have jumped the bounds of Earth and counted the stars, and some of the planets too. We have waded in the vastness of the observable universe. Now, we look homeward. We who have numbered the stars must now take stock of ourselves. We who have explored the possibilities of life in the universe must now ensure the continuation of life on Earth. For this too is humanity's destiny. Bright child of the universe, protector of life.